Tiny bugs show off some seriously insane survival skills when it comes to falling from crazy heights. Like, an ant can tumble from a massive height and just tap the ground so lightly that it doesn't even get a scratch. It totally goes against our human gut feeling that higher falls mean bigger injuries. But ants are just built different because the laws of physics hit way differently for tiny little things. We're gonna find out together why an ant doesn't even need a parachute, and how its tiny size turns a scary fall into just a super chill landing. An ant has a tiny mass compared to its body's surface area. We're talking about an average ant weighing only around 5 milligrams while being just a few millimeters long. This crazy high surface area to weight ratio makes the air feel like a thick, gooey syrup to them, almost like they're swimming through a dense liquid instead of just falling freely. Because of that, the ant slows down the second it starts dropping until it hits a super low terminal velocity. The ant hits its terminal velocity, which is the absolute fastest speed it can reach while falling, in less than 3 seconds flat. For example, if an ant falls from the second floor or even off a massive skyscraper, its speed won't go past a certain fixed limit after that third second. This basically means that falling from 30 meters or just 3 centimeters ends up being pretty much the exact same impact speed. So if an ant drops from literally any height, its terminal velocity only hits about 3.5 to 4 kilometers per hour, which is basically the same speed as a person taking a super slow stroll. Now, a human, our terminal velocity can reach like 200 kilometers per hour, which makes hitting the ground absolutely lethal. Since the ant is moving so incredibly slow, the impact energy is so tiny that it doesn't cause even a bit of damage. As we already know, there are two main forces acting on an ant while it's falling: its weight pulling it down, and air resistance or drag force pushing back up. As the ant picks up speed, that drag force ramps up big time until it's exactly equal to the ant's weight. At that specific point, the ant stops accelerating and just keeps falling at a steady, constant speed. This perfect balance is the secret to why the ant survives every single time. An ant's relatively flat body and those long, sprawled-out legs massively boost air resistance, especially since they spread their limbs wide during a fall to act like tiny natural parachutes. If you compared an ant to another bug with a more streamlined shape, you'd see the ant slows its fall way more thanks to those specific engineering details. It's not just the weight that decides the terminal velocity, the shape and how it's spread out matter a ton. If an ant falls from a crazy high place like a mountain or a skyscraper, it hits its terminal velocity after just a few seconds and then just keeps drifting down super slowly for several minutes. During that long journey, the ant might actually change its direction or scout out a safe spot to land, since it has plenty of time to get ready. That's exactly why an ant's survival rate actually goes up the higher it falls from, which is totally the opposite of what happens to big creatures. Tons of other tiny bugs actually share this superpower too, like little bees and super small spiders also survive falls from massive heights. For instance, a jumping spider that's only 2 millimeters long hits a terminal velocity of just about 2 meters per second. But a small mouse? It reaches a terminal velocity that could totally break its bones because its mass is dozens of times bigger than an ant's. There's actually a direct relationship between the square root of mass and terminal velocity. Scientists actually use super high-speed cameras to film ants falling in the lab, dropping them from different heights up to just 1 meter since they hit terminal velocity so fast. Then they calculated the speed by analyzing the video frame by frame, and they found that the ants weren't hurt at all, even after hundreds of trials. For example, one study dropped carpenter ants from 10 centimeters and then from 10 meters, and the results were exactly the same. Imagine if an ant fell into a jar of honey instead of the air, you'd notice it slows down a massive amount. The truth is, regular air acts just like a thick, gooey liquid for an ant because the Reynolds number, which is a value that determines how fluids behave, gets super low for its size and speed. An ant's Reynolds number is actually less than 10, while a human's reaches hundreds of thousands, and that completely flips the laws of resistance on their head. Just like how an ant spreads its legs during a fall to boost its surface area, it can also use those same legs to soak up the impact of the landing. When it hits the ground, its flexible legs bend just like a spring, which stretches the force of the impact over a longer period of time. Even if an ant drops onto a rock-hard surface like glass, this mechanism cuts the intensity of the hit to less than 100 times its body weight, while their bodies are tough enough to handle forces up to 1,000 times their weight without taking any damage at all. But if an ant fell in a room that was a total vacuum with zero air, it wouldn't face any air resistance at all, so it would just drop with the acceleration of gravity, picking up speed constantly until it hit with a totally lethal force. Luckily, in the real world, an ant never finds itself in a vacuum because air is everywhere. This just reminds us that the exact same laws of physics that rule over rockets and airplanes also rule over the tiniest creatures, just working in totally different ways depending on the scale. Engineers actually took inspiration from this phenomenon to design tiny robots that can drop from massive heights without any parachutes, creating robots weighing just a few grams with wide surfaces to hit a safe terminal velocity. This same idea is used to make sensors that get dropped from drones in dangerous zones. For example, Draper Laboratory developed a robot called Icarus that weighs only 4 grams and can fall from 10 meters without a single scratch. Scientists have measured that ants can actually handle forces up to 5,000 times their own body weight without dying, which is way more than they'd ever face during a normal fall. An ant can carry stuff 50 times its weight while just walking around, but its ability to soak up a massive shock is hundreds of times stronger than that. That's exactly why if you drop an ant from high enough to hit its terminal velocity, it'll survive even if it falls 1,000 times in a row. That insane durability makes ants some of the ultimate survivors in the insect world. So, as we wrap up this breakdown, we can totally see that the secret to an ant surviving a fall isn't some crazy superpower, it's just its tiny size giving the air a chance to slow it down. The smaller a creature is, the more gooey and thick the air feels to it, which keeps that terminal velocity super low. Basically, an ant doesn't go splat because the laws of physics have its back when you're that small. It really makes you realize that the true masterpiece is how every little creature is perfectly built to handle its world down to the very last detail.